So let's take a look at vector fields. Now vector fields are very similar to slope fields in that we're trying to plug in different xy values to find out what the components of the vector are at different points. So for this first set of problems, let's go ahead and sketch the vector field f. So for number 1, we have f of xy equals 1/2 times I plus j. So I plus j are those unit vectors, so I'm going to start by distributing over the 1/2. So we get 1/2 I plus 1/2 j. Now if I go ahead and write this in component form, we can write it as 1/2 comma 1/2. So let's go ahead and make a vector field for this. So I'm just going to make the x values range from -1 to 1, and the y values also range from -1 to 1. So all we have to do is plug in different points and see what the vector is at each of those points. But since there are no variables in the vector, this tells us that no matter what xy value we plug in, so at every single point, the x component is going to be 1/2, the y component is going to be 1/2. So let's just start with 0, 0, x component 1/2, y component 1/2. The vector is going to look like this. At 1, 0, it's going to look the same thing. At -1, 0, same thing. At 0, 1, same thing. And at 0, -1, the exact same thing. And at all other points. So this is going to be an approximate vector field for this first problem. So now for number 2, we have f of xy equals y times I plus 1/2 j. So if I were to go ahead and write this in component form, we have y as the x component and then 1/2 as the y component. So once again, I'm going to go ahead and draw a coordinate plane here. X values range from -1 to 1, y values the same. So we can just plug in different points. So let's just start out with the origin at 0, 0. So when I plug in 0, 0, I'm going to plug in the y coordinate for that y value there. And so the x component is going to be 0. And the y component is still going to remain the same 1/2, because 1/2 is just a constant. So at the point 0, 0, the x component is 0, the y component is 1/2. Now since there's only a y variable in the vector, this tells us that if two points have the same y variable, or the y value, so let's say we pick the point 1, 0, we're also going to get the vector 0, 1/2. And if we pick -1, 0, we're also going to get 0, 1/2. So it's going to be the same vector at similar y values. Now if we go ahead and pick the point 0, 1, our vector will then be 1, 1/2. So the x component is 1, the y component is 1/2. So the vector will look something like this. And the same thing goes with -1, 1, and also at 1, 1. Now if we go ahead and plug in 0, -1, our vector will then be -1, 1/2. So the x component is -1, the y component is 1/2. So the vector will look something like this. Once again, same thing goes with 1, -1, because it has the same y value, and the same goes with -1, -1. So now for number 3, we have f of xy equals y times I plus x times j over the square root of x squared plus y squared. So let's go ahead and just put the numerator in its component form first. So I can rewrite it as in component form y comma x, and then we have y comma x over the square root of x squared plus y squared. I can go ahead and divide each of the components by the denominator. So then we will get in component form, the x component is going to be y over the square root of x squared plus y squared, and the y component is going to be x over the square root of x squared plus y squared. So once again, I'm just going to go ahead and graph this and pick different xy coordinate points. So let's go ahead and just start with the origin at 0, 0. But realize when I plug in 0, 0, we'll end up dividing the denominator by 0. So this tells us that the vector at 0, 0 does not exist for this specific example. So let's go ahead and pick 1, 0 this time. If I pick 1, 0, we will then get 0 as the x component, because the y value is 0. If we plug that in for y, we'll get 0, comma, the y component is going to be 1 over the square root of 1 squared plus 0 squared, so the square root of 1, which is 1. So we'll end up getting 0, 1. So at the point 1, 0, the x component is 0, the y component is 1. So now let's go ahead and plug in -1, 0. When I do that, the x component will be 0, and the y component this time will be -1 over 1, so -1. So at the point -1, 0, the x component is 0, the y component is -1. So now if I go ahead and plug in 0, 1, this top point here, the vector will then be 1 over the square root of 1, which is 1, and then comma 0. So we get 1 comma 0. So at the point 0, 1, x component is 1, y component is 0, and if we go ahead and plug in 0, negative 1, the x component will be negative 1, and the y component will be 0. So it looks something like this. So now for number 4, we have f of x, y, z equals j. So realize this is 3 variables. Now in the previous problems, we only had 2 variables, x and y, and we could graph that in 2 dimensions. Now since we have 3 variables, we have to use a 3-dimensional coordinate system and a 3-dimensional graph. So writing this in 3-dimensional component form, since j is associated with the y component, it's just going to be the unit vector 0, 1, 0. So once again, drawing this in a 3-dimensional coordinate system with the x, y, and z axis. Now, no matter what value we plug in for x, y, and z, it is always going to be 0, 1, 0. So that is always going to be the vector's components, which means the x component is 0, the y component is 1, and the z component is 0. So everywhere the vector is going to be the exact same thing. Now the next set of questions are going to be about finding the gradient vector field. So remember the formula for the gradient vector given a multivariable function f of x, y. So the formula is going to be equal to the partial derivative of the function with respect to x times I plus the partial derivative of the function with respect to y times j. So in its component form, we can also write it as f sub x comma f sub y. So for number 1, let's go ahead and find the gradient vector field of f. So f of x, y equals the natural log of x plus 2y. So let's go ahead and first find f sub x, or the partial derivative of the function with respect to x. So since we have natural log of some function, the partial derivative with respect to x is going to be the derivative of the inside function, which is going to be 1 if we partially derive with respect to x, over the inside function, which is x plus 2y. Now f sub y is going to be the partial derivative of the inside function with respect to y, which is 2, over the inside function, x plus 2y. And so if we rewrite the formula, you get the gradient vector of f of x, y is going to be equal to 1 over x plus 2y times I, because it's the x component, plus 2 over x plus 2y times j, because it's the y component. And that's the final answer. So now for number 2, we have f of x, y, z equals the square root of x squared plus y squared plus z squared. So realize we do have 3 variables this time. So the gradient vector formula is going to look a little bit different. We're just going to have to add that z variable. So we have f sub x times I plus f sub y times j. Since we have the z variable, we have to add f sub z plus k, because that's going to be the z component of the vector. So I'm actually going to go ahead and rewrite x squared plus y squared plus z squared as this, but to the 1/2 power. Because when I find f sub x, f sub y, and f sub z, I can use the chain rule. So f sub x, or the partial derivative of the function with respect to x, is going to be 1/2 times x squared plus y squared plus z squared to the negative 1/2 times the derivative of the inside function with respect to x, which is 2x. 2's will cancel, and so we're left with x over x squared plus y squared plus z squared to the 1/2, or the square root of x squared plus y squared plus z squared. So now let's find f sub y. So the same process here, we're still going to use the chain rule here. So x squared plus y squared plus z squared to the negative 1/2, and then times the partial derivative of the inside function with respect to y, which is 2y. Notice the 2's will cancel, and so we're left with y over the square root of x squared plus y squared, and then plus z squared. And so f sub z, we can skip a little bit of work here because it follows the exact same pattern. Instead of x on the numerator and y on the numerator, this time we'll have z on the numerator over the square root of x squared plus y squared plus z squared. So if I go ahead and write the formula for the gradient vector field of f in terms of 3 variables, x, y, and z, we're going to get x over the square root of x squared plus y squared plus z squared times I, because that's the x component, plus y over square root of x squared plus y squared plus z squared times j, because that's the y component, and then plus f sub z, which is z over square root of x squared plus y squared plus z squared times k, because that's the z component. And that's going to be the final answer. So now for number 3, we have to find the gradient vector field and also sketch it. So we have f of xy equals x times y minus 2x. We do have two variables, so we can use a simplified formula here that we used in the first problem. So f sub x, or the partial derivative of the function with respect to x, is going to be y minus 2. And f sub y, the partial derivative of the function with respect to y, is just going to be x. So rewriting the formula for the gradient vector, it's going to be equal to f sub x, which is y minus 2, times I, plus f sub y, which is x, times j. Now I'm going to go ahead and first, before sketching, write it in component form. So we have y minus 2 as the x component, and then x as the y component. So now let's go ahead and graph this. So since there's only two variables, x and y, we only need two dimensions. So I'm going to go from -1 to 1 for the x values, and from -1 to 1 for as well for the y values. So let's go ahead and start with 0, 0. If I plug in 0, 0 into the vector here, we will then get a vector of 0, minus 2, negative 2, comma 0. So at 0, 0, the x component is going to be -2, and the y component is going to be 0. Now if I try plugging in 1, 0 into the vector, we'll get 0, minus 2, negative 2, so that's the x component, comma 1 as the y component. So at the point 1, 0, the x component is going to be -2, and the y component is going to be 1. So it's going to look something like this. Now let's try plugging in 0, comma 1. So in this case, we'll get 1 minus 2, so -1, comma 0. So at the point 0, 1, the x component is -1, the y component is 0. It looks something like this. Now I'm just going to go ahead and plug in one more point. So let's try 0, -1. So when I plug in -1 for y, we'll get -1 minus 2, -3, comma 0. So at the point 0, -1 is probably going to extend beyond the screen. We'll just have the x component of -3 and the y component of 0. So it's just going to end up passing the screen here, way to the left. So this is what a gradient vector field could look like for this specific problem.